In this video, we'll explore some foundational concepts behind hypothesis testing. Recall that whereas exploratory questions ask about what patterns we observe in our sample data, inferential questions ask, in light of the potential error in our sample estimates, what can we conclude about the broader population of interest? We've explored how confidence intervals can be used to answer such questions. Next, we'll examine how we might follow up a confidence interval analysis with a formal hypothesis test. For example, suppose we're interested in whether there's a significant positive association between daily bike share ridership and temperature. The actual relationship between these two variables can be represented by the following formula, where the actual intercept beta 0 value and temperature coefficient beta 1 value are unknown, since we don't have all possible data points. Instead, to make inferences about this relationship, we take a sample of data on 50 different days. Notice that the confidence bands around our estimated trend don't include a zero-slope line, indicating significant evidence that ridership does indeed tend to increase in warmer weather. As a follow-up to this observation, we can also examine a 95% confidence interval for the beta 1 temperature coefficient. A quick but rough confidence interval is calculated by taking our coefficient estimate, 50.64455, plus or minus 2 standard errors of 13.34735. A more exact result is provided by the convint function, and this result indicates the following. We can be 95% confident that for every 1 degree increase in temperature, the typical increase in ridership is somewhere between 24 and 78 riders. The fact that this confidence interval lies so far above zero, and that our confidence bands don't include this zero-slope line, provide ample evidence of a positive association between ridership and temperature. Alternatively, we could answer our inferential question about the relationship between bike ridership and temperature using a formal hypothesis test. Now, there are countless types of hypothesis tests. It's impossible to cover every one in this course. It's also quite unnecessary. We'll instead focus on the common structure among all hypothesis tests. Doing so will allow us to generalize these concepts to any hypothesis test, both those within and beyond this course. This common structure consists of 3 steps. Let's focus on the first step first. The first step of a hypothesis test is to specify what hypotheses are being tested. In general, there are 2 competing hypotheses. The first is the null hypothesis, denoted by H0 or H0. This hypothesis represents the status quo, or no effect. It's basically the boring hypothesis. The null hypothesis is contrasted by the alternative hypothesis, denoted by HA. This is the hypothesis which states the actual claim we're making about the population. Throughout the remaining steps of the hypothesis test, it's critical to consider that tests are like the justice system, operating under the idea of innocent until proven guilty. That is, we go forward in our analysis assuming that the status quo null hypothesis is true, and put the burden of proof on establishing the claim in the alternative hypothesis. As an example, recall our goal to assess whether there's a positive association between ridership and temperature in the population model. In specifying the hypotheses of interest here, it can be easiest to start with our actual claim, the alternative hypothesis. Translated into notation, our claim that we want to test is that the temperature slope coefficient is positive. In contrast, then, the status quo hypothesis is that the coefficient is 0. That is, that there's no association between ridership and temperature. With these hypotheses in place, let's move on to step 2. In the spirit of innocent until proven guilty, we must compare our sample results to what we'd expect under the null hypothesis. That is, we assume that the null hypothesis is true and question how compatible our sample data is with this hypothesis. To this end, recall our sample model. In particular, note that our estimate of the temperature coefficient, 50.64, has a potential standard error of 13.35. As such, the central limit theorem provides the following approximation of the sampling distribution of the sample temperature coefficients. Mainly, we can assume that the sample estimates are normally distributed around the actual temperature coefficient beta 1, which we don't know. And the range of these possible estimates is indicated in terms of being within 1, 2, or 3 standard errors from the actual coefficient of beta 1. Now, if we assume that the null hypothesis is true, that is, that the actual temperature coefficient is 0, this means that we would expect the sampling distribution to be centered around 0. That is, we'd expect the possible sample estimates of the temperature coefficient to be centered around 0, or normally distributed around 0, and range from roughly negative 40.05 to positive 40.05, a range that's within 3 standard errors from 0. Notice that within this hypothetical sampling distribution, under the null hypothesis, our sample temperature coefficient of 50.64455 falls way out in the tail. That is, our sample estimate is much larger than we would expect to see if in fact there were no relationship between bike ridership and temperature. That is, if the null hypothesis were actually true. Or another way to think about this, our sample data is not compatible with the null hypothesis. At this point, we have a powerful result, but our observation is somewhat subjective. It's critical that we're able to specify and communicate just how incompatible our data is with the null hypothesis. To this end, there are a couple of approaches. First, we might calculate the distance between our estimate, 50.64455, and 0. That is, to calculate how far is our estimate from 0. Since the scales of model coefficients will vary from analysis to analysis, depending upon what we're measuring and modeling, it's best to calculate this distance using a universal z-score approach. Here, by subtracting 0, the hypothesized value, from our sample estimate of 50.64455 and dividing by our standard error of roughly 13.35, we calculate that our sample estimate of beta 1 is 3.8 errors above 0. By the 6895-99.7 rule, we know that 3.8 standard errors is quite far. Also, in making this calculation, notice that subtracting 0 doesn't actually do anything to our calculation mathematically. It merely reiterates that in our hypothesis test, we're comparing our sample estimate to the null hypothesized value of 0. Further, take note that this type of calculation has a formal name. The result is called a test statistic. Tough for me to say. Now, in addition to calculating the distance of our sample estimate from 0, or the test statistic, we can calculate the probability of having gotten an estimate so far or even further from 0. To this end, if the null were indeed true, that is, if in fact beta 1 is 0, the 6895-99.7 rule indicates that the probability of having gotten an estimate that's more than 3 standard errors above 0 we know this has to be less than 0.0015. That is, it would be possible but very, very unlikely that we would have observed such a strong association between ridership and temperature in our sample data if in reality there were no relationship. This type of probability calculation has a formal name. It's called a p-value. Bringing this together, we've learned two approaches to measuring the compatibility of our sample results with the null hypothesis. In general, a test statistic is a one-number summary that measures the compatibility of our sample data with the null hypothesis. For example, for tests of model coefficients, as in our bike ridership example, the test statistic will measure how many standard errors our estimate falls from 0. Further, a p-value measures the probability of observing our sample results by chance. That is, the probability of observing a test statistic or a sample estimate as or more extreme than ours, if in fact the null hypothesis were true. And here, when we say as or more extreme is defined relative to the alternative hypothesis. In our example, extreme meant far above 0. But though they can be handy, p-values can also be notoriously misleading, often because they're simply misinterpreted. To this end, it's important to remember that the p-value measures the compatibility of our data with the null hypothesis, not the other way around. It speaks to the uncertainty in the sampling process, not the uncertainty in the population. Thus, as tempting as it can be, the p-value cannot be interpreted as the probability that the null hypothesis is true. That hypothesis is either true or it's not, with probability 1 or 0. Now, even though this is not how we can interpret a p-value, it is a very common and consequential mistake that's important to keep in mind moving forward. Now, before moving on, notice that this test statistic and p-value for our test of an association between ridership and temperature are reported right in our model summary table. First, notice that the t-value column is the result of dividing our coefficient estimate by its standard error. That is, the t-value column reports our test statistic. Our sample estimate is 3.79 standard errors above 0. Next, when divided by 2, the final column reports the p-value for our hypothesis test. This p-value is more accurate than the one that we approximated using the 68, 95, 99.7 rule. It indicates that if in fact there were no relationship between ridership and temperature, there's only a 0.0002 chance that we would have observed such a strong positive association of 50.64 between these two variables in our sample data. As an important aside, note that we're only dividing by 2 here, since we're testing a one-sided alternative hypothesis test, or a one-sided alternative hypothesis, that there's a positive association, or beta 1 is greater than 0. We would not divide by 2 if we were testing a two-sided alternative hypothesis, that there's any association, either positive or negative. That is, that beta 1 could be positive or negative. It doesn't matter. Beta 1 is not equal to 0. Finally, taking into account what we learned in step 2 about the compatibility of our sample data with the null hypothesis, we can make some conclusions. The counter to what you might have learned in the past, and counter to what some people would like, forming a conclusion is a very nuanced process. Hypothesis tests typically don't result in clean, binary yes or no decisions. Thus, here are some guidelines for forming some sort of conclusion. First, we can examine the size of the p-value. Small p-values indicate that sample data like ours would be uncommon if the null hypothesis were true. Thus, our data are not compatible with the null hypothesis. In contrast, Large p-values indicate the data like ours would be typical if the null hypothesis were true. Thus, our data are compatible with the null hypothesis. Second, we can determine the presence or absence of an effect, or the presence or absence of a relationship. To get a sense of scale, people often compare the p-value to a chosen significance level, often 0.05. They do so to determine whether our data provides sufficient evidence against the null hypothesis. For example, if our p-value is small enough that it falls below the 0.05 threshold, we can say that our results are statistically significant at the 0.05 level. In contrast, if our p-value lies above this threshold, or our data isn't that incompatible with the null hypothesis, our results are not statistically significant at the 0.05 level. Finally, and importantly, it's important to remember two things. 0.05 is not some magic cutoff, and statistically significant results aren't necessarily meaningful. To this end, using just the above guidance would produce an incomplete conclusion. P-value analyses must be supplemented with information about the magnitude of the sample estimate and its corresponding sample error, or standard error. That is, not only is the relationship not zero, we want to know if the relationship is big enough to be practically meaningful in the context of our analysis. In conclusion, throughout our analysis of bike ridership, we've shown that the relationship between ridership and temperature is both statistically significant, for example, the p-value is quite small, and it's of a meaningful magnitude. For every 1 degree increase in temperature, we expect 51 extra riders, with a standard error of 13 riders per 1 degree increase. On the scale of bike share ridership, this change is quite large.